Okay, so welcome everybody. It's my pleasure today to introduce Xenia Miscouridou. She has been doing she was a PhD at Oxford, so you might have seen her around Warwick or Oxford. And since 1 month ago, so since last month, she's now at Imperial. And today she will talk about Bayesian nonparametric for sparse dynamic graphs with reciprocating relationships. Please go ahead.
Thank you. Thank you very much, Asim, for the intro and for the invite. So, yeah, I will present some work I've done during my PhD back in Oxford with my advisors, Francois, Caroline, White. And it's about how we use Bayesian nonparametric tools and point processes, actually, to be more precise, to model networks. So to model the connections between the people and reciprocating relationships between them. And of course, I will explain this more in a bit. So my plan is the following. I will start giving some motivation about the exact problem and setup I'm interested in. Then I'll focus on two different aspects. So the first one is the local properties that I care to model, so between any two people. And then the global properties. So global in my case is a whole graph. So it's a picture of a graph in time. And then I will explain how we perform inference in this setting, always Bayesian, and how good this is. How does it perform? So the motivation. The setup I'm interested in is the following. I want to model temporal interaction data that come in the form of triplets. So I have the form IJT, meaning that there was an action from I towards J at time t. So there is a direction and there is time. So time-stamped interactions in other ways. So we observe, this sort of data in various fields, like in social networks. So when people send messages or emails or any sort of actions between them. In biology, there are data. I think like in proteins, there is evidence of this type of behavior. In neuroscience, we have neurons that excite each other, firing against each other, and we have time-stamped interactions. But in all these cases, we are interested in answering questions like, which are the factors that underpin these interactions? For example, how often do we expect them to interact with people? And of course, if we zoom out and we just view this as a big graph, as a whole network, which are the properties that we observe in this, in this big graph? What is the structure of this big graph? And of course, always, what we do, at least how I do things is that we want to have a model to explain the patterns, explain the structure, but also have a way to do prediction. For instance, in this case of network data, we want to predict future links. And then, according to the context we are in and the scenario and the data, we want to use that, make something useful out of it and assist in some sort of decision making or measure, an intervention effect and see, if you remove this sort of, part of your network and people, what changes. So temporal interaction data is what I'm interested in. And I'm going to focus on a simple example, a toy example, just to bring more context here. This is a subset of a data set I worked with that was about students in a college that exchange messages between. It's like an internal college Facebook type of thing. And the time, the numbers on the arrows are the times in which these two people exchanged messages. So firstly, we have B, and then B sent a message to A at this relative point time 2.1. It's just because I normalize them that, you see these weird numbers. And then B sent another message. And then A finally responded at some point. And then B sent another message. A responded. A sent another one. B sent another one, 0.8.1. And then, a final one. So in this fixed time interval of 10 hours, there were these messages exchanged in these directions. So what is the key property that I want to model? And I try to show you with that toy example. So the property I'm interested in is what we call reciprocity or reciprocation, which means that a directed action from A to B increases the chances of a similar action being returned in the near future. So it's very obvious in this toy example I use, because if I send you a message, I'm saying that it's highly likely that you respond in the future. And this is what I want to do. How do I model it? I model it using point processes, and particularly inhomogeneous point processes in the family of Hawkes processes. So to give it like a very brief, intro and definition of the Hawkes processes, there are two objects I'm interested in: the counting process, capital N of t, and the conditional intensity process, lambda of t. So with capital N of t here, I will denote the counting process. So we just count how many events have occurred up to time t. So before up to time 10, there were 10 events, so something like that. But of course, what drives the counting process is the intensity. So lambda of t is the intensity, which is the key ingredient that will decide when another event is happening. So I draw here, I'm saying that N of t is a realization from my Hawkes process with that conditional intensity. And with that second equation here, I'm just showing the definition, saying that the probability of having another event from my point process in an infinitesimal point in time dt, conditioning on the history, is lambda. So the probability of another event is proportional to lambda, but everything is conditioned to the history. That's what makes this inhomogeneous. So that's how a single Hawkes process works. But what I really want to do here is I want to model pairs of people. So I said that I have a pair of people and events from one towards the other, and encourage events from B to A. So A to B, encourage events from B to A. So I have mutual excitation. So in order to explain and model this mutual excitation between a pair, I need to explain two processes. So I need two Hawkes processes here. So I will denote by capital N of AB the process of events from A to B, and with capital N of BA the process of events from B to A. So that's that's simple. But now, how am I going to encode the behavior I'm interested in? That I want to say that the probability of me sending you a message depends on whether you sent me one in the past. So, and this behavior I'm encoding in through the conditional intensity. So the first equation here, which is the intensity for events from A to B, is some constant nu plus this integral of a function integrated over the other process. So the opposite process. You see that the intensity of A to B is a functional integrated over this capital N of BA. So this is saying, the interpretation of this is that the probability of A sending another email to B at time t depends on the emails that B sent to A in this whole time from 0 to t. And the same thing in an analogous way is for the second equation here, lambda B to A. So, and as you can see here, I have this function g, this kernel g, that I'm not, haven't defined yet, but the form of this kernel g will determine whether, whether the emails of B to A have influenced me, whether they are very recent or, whether they have happened ages ago. So with the form of G that I will choose, I will show that, if you emailed me yesterday, it's different, like your impact on me is different whether you emailed me, 10 days ago or 10 years ago. So in other words, by choosing G, in my case to be exponential, later on, I'll show in a bit, I'm saying that it's highly likely that I send you another email if you emailed me recently. So I think if I go back to this example, it's always better to show things graphically. So here I have simulated from my processes, and I have on the top row the counting processes, and on the bottom row the intensities. So you should be looking at this diagonally. And if we start from the top left, here I have the counting process for all the events from A to B. So you see that A sends a message to B at the point 5 point something in the top left. So then the counting process increases by 1. So this is just a step function going up by 1 every time A sends a message to B. So what's the interesting thing? The interesting thing is to see the impact. So now we go like to bottom right, and we see that the minute that A sent a message to B, at 5.6, then the intensity of B instantaneously has a spike, if you see at the bottom right graph, which is saying that once A sent this email, then instantaneously B is very likely to respond. But then as time goes on, this probability decreases. And then at this next message at 0.7 or something, again, the probability of B responding is very high. There is this spike, and then it goes down. So the choice here, the choice of my G function was an exponential function, showing this exponential decay that you see here. So if this is saying that, if I don't reply to you, then I may, not reply, ever. So the probability of response really goes down, exponentially fast with time. And of course, here, this is just a choice. This is just a choice because this is what, these social data sets looked like, but it doesn't have to be, according to the data set and the context you're interested in. A different choice of a G function, of a kernel function can be taken. Yes. So if we're fine with this graph, then I would move on to getting a step back, because whatever I have explained so far and I have shown you here is for a single pair. So how do you model a process from A to B and a process from B A in the single pair of people? But we have a global graph. So we have like these people belonging to a social network, or it could be a collaboration, a transplantation, and other sorts of professional networks. So we want to model every single pair in this network. So you see AB here was, the set, the example I showed you before. And again, this is, a toy example, super small, just, 5 people. But, the point is that regardless of how, big your network is, you really need to model every single pair of people, and there are processes between them, the interaction between them. So nothing really changes in the model setup. Because before I had AB, so I had capital N of AB, and now I have IJ. So for every directed pair in my graph, IJ, I denote by N of IJ the counting process for all the events from I to J. This counting process will have the intensity process lambda ij. And again, as before, we have nij and nji being mutually exciting. And we model that mutual excitation via the definition of the conditional intensity. So this is the same slide as a couple of slides ago where I had AB. So you see here that lambda ij, the intensity from I to j, is some constant mu. It's mu ij, but it's the same as mu ji, so you can just call it mu, plus this integral over this function g, integrated against the opposite process n of ji. And of course, if we want to take, a discrete approach to this, the equivalent of this in integral would be, a sum of this function g evaluated at every point in time where there was an event from the opposite process. So this is the setup. So pairs, I'm using pairs of Hawkes processes to model pairs of interactions between people in a network. But I haven't really talked about, what is the graph connection. So we can all see that these ij's and ji's are just, pairs in the graph. But the whole point is that, in order for people, and an assumption here is that in order for people to exchange messages, to exchange emails and everything, is that they are initially connected. So in this, Facebook example I like to use is that in order for two people to start exchanging messages, they need to be initially, friends in this social network. So in my model before, this mu ij, this constant part in the intensity of the Hawkes process, is the probability of connection. So it's proportional to the probability of connection. So it says that, of course, that has to be positive in order for the Hawkes process to exist. So in other words, we have to be connected in order for us to exchange messages. So this mu ij is the part that connects us to the graph. So when I say graph, I have explained how I model the direction and the times of the events between any single pair. So now I care about how people and how nodes are connected in the first place, and also how which are the properties that I observed and I'm interested in modeling through that mu ij. So whatever I'm going to explain now is just is modeled via the parameterization of my mu ij parameter in the conditional intensity. So through those base intensities, through the parameterization of those, we particularly, target these 4 properties in a graph. The first one is assortative mixing. So we assume that the more similar the nodes are, the more likely it is that they are connected. So the way we connect that is that, in our underlying assumption is that there's also a latent process that shows, how people have affiliations and, how they are split in different groups. And we're saying that for 2 people, in order to actually connect in a network, they have to be, similar. So the more similar they are, the more similar their affiliations are, the more likely it is that they connect in the first place. And afterwards, they can start sending messages and everything. The second crucial property we're interested in is the power law degree distribution, which says that the behavior we observe when it comes to the degree distribution, and just aside here, the degree of a node, so the degree of a person, say, is the number of edges attached to it. So it's the number of friends I have, in Facebook, for instance. So we observe some nodes have like a large number of connections. These are the influencers, let's say, in a social scenario. But at the same time, a lot of them, and actually most of them, have very, very few connections. And when I say few, a few can be 1. So you see that the degree distribution I'm talking about is a heterogeneous degree distribution, the extremes. And this is not trivial to have in a model. It's very desirable because this is what we observe in social networks. And the way we model and parameterize mu ij has to be in a way that meets a parallel degree distribution. Now, the third property I'm interested in when it comes to the global graph is that I need that to be able to be sparse or dense. So when I say sparse or dense, so a graph is sparse when the number of edges grows subquadratically with the number of connections in the graph. Whereas a dense graph is a graph, where the number of edges is quadratic in the number of nodes. And again, what we observe in big data sets, in network data sets, of course, and in social scenarios that I was particularly interested in, is that the graphs are sparse. They tend to be sparse, and of course, the sparsity also connects to the power law degree distribution that I talked about. So, when we observe these sparse graphs, it's the case where we observe these, big hubs, the influencers, coexisting with the other nodes that have like very, very few connections. And like the final point to show here is that the framework in which we model these mu ijs is so that we want to keep exchangeability, underlying exchangeability. In other words, probabilistic symmetry. So we want to say that the distribution of our graph here is invariant to permutations of the nodes. And like the reason that we take this like the Bayesian nonparametric approach is because it's and the different representation we take is so that we can achieve these properties, the sparsity and the power law, with this exchangeability. And I'm very happy to elaborate more on that, perhaps afterwards. Now, I don't really want to get into the details of this mu ij component here, but apart maybe from this one, that mu ij is the part that is responsible the interactions from I to J, and it's that have to do all these properties with sparsity and heterogeneity and so on and so forth. And in order to bring some more like a bayesian nonparametric flavor in here, I need to say that these mu ij's are essentially the dot product of two vectors that are realizations of compound completely random measures. So to be more clear, the setup I'm interested in is that I consider vectors of completely random measures. And every person or every node, every component in my network has its own vector. And everyone has a vector of size p, because I assume that there are p communities in the network. And the way I model the link probability is proportional to this dot product. So you see W, the sum of Wik, Wjk. So we're saying that these Wi's, these vectors are showing the affiliations to these latent communities. So Wik is the level of affiliation of person I to community K. And since I'm taking a dot product between your vector and my vector, this is exactly saying that the more similar we are, the higher the probability that we are connected. So we model communities in this way, and we model, homogeneity and assortativity in this way. So, I mean, this is the main. When I talked about parameterization of mu ij, this is the main part behind. I'm not going to go into the details of the compound completely random measure, like simulations and everything. Happy to come back to that later. But I want to, so far, I've summarized essentially how this model works. So Hawkes processes for every pair, but the component of this conditional intensity Hawkes process connects back to completely random measures and how you formulate the graph. But always an interesting question is, okay, this is nice. This is like fancy math sometimes, but how do you perform inference and how can I learn with it? So now, the setup I'm interested, of course, is, what I observe is a set of these interactions, ijt, and I want to estimate all the parameters that have to do with the Hawkes part, so the time-dependent part, and also all the parameters that have to do with the graph part, the mu ij part. So what this slide here is trying to say is that I have these two sets of parameters. Okay, so the time, the kernel parameters that tell me, how fast in the future you are expected to reply to me, or, are you ever going to reply to me? And then we have, the X parameters, which are the graph, which are connected to the mu ij's and everything. And it turns out that, it was difficult to have, so I'm always taking, a Bayesian approach based on sampling. And it was difficult to have, a full keep sampler updating all these parameters, sequentially, but, in the same sampler. So what we came up with, it was this approximate posterior to do that, that we call a two-stage approach, a two-step approach. So I am talking about this here. So my two-stage inference is motivated by modular Bayesian inference. There was, this paper by Jacob and al. That initially inspired me to take this approach. And what this is saying is that, okay, there are two sets of parameters to estimate. Okay, two families of parameters. And what I'm going to do is that I'm going to firstly estimate the first set, in my case, the graph set. So I'm going to estimate everything that has to do with the link probabilities and the global graph structure, the parallel, the sparsity, and all these things. And then conditioning on a point estimate of those, I will estimate the other parameters, which were the kernel one, the exponential kernel function g I talked to you about. So everything that has to do with time. So you see that conceptually, this makes sense in the sense of you first form a graph and then you start having connection between the people. So the main motivation behind doing this approximate inference was, of course, to have a faster algorithm, more efficient, so that we can, use it in several applications. And also we already had, some good code for performing, the first step on its own. And we had this MCMC algorithm that was a linear per node and edge, linear per edge of the graph in order to estimate the graph structure. So that was quite fast. And then, just estimating the kernel parameters of the Hawks process on top was, which is a second step, nice and fast. So we were happy with it. And I can show you at the end some, empirical posterior consistency checks we did to make sure that, at least empirically this makes sense, that the posterior would converge to the true value under, more and more samples. But it's only empirical, it's not theoretical. I guess it would be cool to have a theoretical justification as well of this modular approach. And I guess overall, if I take a step back, like, why do I care about this model? And of course, what does it learn? As I said, firstly, it would learn the global graph structure. So when I estimate my vector parameters for every node, I could do some community detection and see, how much affiliated am I to each community. So then I could, take my highest affiliation and say, okay, then I belong to this group. Similarly, I could see how the degree distribution looks like and see if we have this phenomenon called rich get richer, which is, the phenomenon I told you about, the, having hubs, like hubs of in the graph, meaning like a person with a huge number of connections. And then, if you have some extra information and some context, you could try to interpret it in the context of the data. So all of that about the graph. And then at the second step, we learn the reciprocation effects. So in the example of emails, messages, the question is, okay, how, once I send you an email, how strongly affected are you? So how big, how high is that spike in your intensity when you receive a message from me? And this, directly says how likely you are to respond. And the other aspect I'm interested in is, okay, once I send you a message, will you respond to me? And like, if yes, when? How fast does this effect decay? So if you don't respond to me tomorrow, will you respond to me, the day after? And then, maybe never. And of course, this scenario I explained was, I would say, was a very simple, like basic scenario. You can make it more, personalized. If you say, okay, it depends how fast I respond to an email, depends who sent it, or depends, the person who sent it, which are his affiliations and his groups, and there are, all these things that you could do and make it more realistic in the scenario you're interested in. So yeah, using this modular scalable Bayesian inference, we could make it quite fast. And what made the first part fast, like the graph estimation, what made that linear in the number of edges was the fact that we use a Hamiltonian Monte Carlo algorithm instead of just, Metropolis Hastings. And finally, the way, I would, evaluate this model, of course, first, I would see, okay, do these, does my posterior distribution reflect the properties I know that exist? What are the communities that I have uncovered? Does this match, the ground truth information I have? So the first thing I want to see, if I can explain the model, if it makes sense. And then secondly, I can use for prediction and like forecasting. So I would split my data set in training and test, and then according to all the parameters I have estimated in the first part, can I use those to predict the number of messages exchanged between every single person in my network in the future? So this is what I do, and compare it to other models in literature. So I simulate from the model, and I take a root mean square error of the true number of links, because I have them, and the estimated ones, and I see how good this is. And the yes. So actually, I mean, these numbers here don't really make sense, but on the table on the left, but this is just the difference, the mean square difference between the true number of links, so the sum of all the links between all the pairs, and the predicted ones from the model. So there are, I mean, this is compared across two different benchmarks, but also, a very, I would say, competitive model in literature. The one I call Hox IRM. And, we would see that, this model, okay, performs better, but of course it also captures, more properties. So all these properties that I'm interested in, and I observe them in the social network scenarios. These are all captured by the first model, whereas the rest are missing one or two, depending on the setup. And yeah, I guess just a final slide here is that if I put let's say my more academic scholar hat on, I like this model because it generalizes existing models that deal with excitation and mutual excitation, but we generalize this in the case where the networks have power law and are sparse. So it's in this way it kind of unifies these two worlds. So the mutual excitation, the reciprocating relationships, to the case that graphs are sparse. At the same time, since this model, this family of models deals with local dynamics, pairs, and also global, like a full graph, it's pretty useful in order to combine these two worlds, large scale, small scale, in a unified framework, and without having to have extra parameters. Now the third one is relates to a comment I made before, that you can make it as personal you want. So by choosing a different kernel function than an exponential, by making that by making the parameters of the kernel different per pair or different per community, you can encode the properties you want in a more personal way. So in my case, in the data sets that I worked on, I would always see and also assume that there is a global behavior of people. So on average, in that data set of an organization, everybody took a similar amount of time to respond to an email. So it didn't make sense to have everybody having a different parameter for that response time. But of course, this doesn't have to be the case in any kind of random scenario. So you could say that my response time depends on who sends that email, what time of the day, what are the affiliations of the person. So it's I describe the more basic, broad scenario that you can personalize. And of course, okay, the last one, I'm not saying that this is causal learning, but we can use it aside with causal learning and say, okay, we know here that this process excites this other process, but we don't know if it's a causal relationship, or there is something else that exists out there and causes this excitation for for both. So perhaps with that. Some more information, or assuming another kind of latent process, we can see that there is some causal relationship to infer here. And I think this brings me to the end. But please, your questions are very welcome, and thank you very much.